All right, so in Chapter 11, Section 4, we're going to be talking about two different types of tests to determine if a series converges or diverges. And so they are both going to be forms of the comparison test. So the first one we want to talk about is just the direct comparison test. And the big idea is to compare a series with a known series that converges or diverges. So if we look at our sheet, we've talked about our p-series, our geometric, we did the integral test last time, and now we're on to our next two, which are going to be the comparison test, and then we'll do the limit comparison a little bit later on. So the idea with comparison is exactly what we were saying, is we are wanting to compare the series that we're looking at with a known series. So the comparison test can work two ways. So if we look at the general term of our sequence, so the first thing we'll notice is in both of these tests, all of the terms of the sequence must be positive. So if 0 is less than an, and an is less than bn for all n, and bn converges, then the series of ANs also converges. Similarly, if AN is bigger than or equal to BN, which is bigger than or equal to 0, and we know BN diverges, then AN also has to diverge. So basically, if all of the members of a sequence are less than all of the members of another sequence that is known to converge, then the first series must converge. If all of the members of a sequence are bigger than a known divergent sequence, then that series must also diverge. So that's the idea of comparison. So let's take a look at a couple of examples. So example 1 with a few different parts. We want to determine if the series converges or diverges. So we take a look at our series, and we have the sum as n goes from 1 to infinity of 1 over 2 to the n plus 1. We look at this, and this is a very informal way to say it, but this is almost geometric. In fact, if it was 1 over 2 to the n, then it would be geometric that would be the same as 1/2 to the n. So that would be our r to the n, and it would be exactly a geometric series. But by comparison, we know that 1 over 2 to the n plus 1, since this is in the denominator, if you make the denominator bigger, it makes a fraction smaller. So 1 over 2 to the n plus 1 is less than 1 over 2 to the n, which is equal to 1/2 to the n. So then this gives us that 0 is less than or equal to 1 over 2 to the n plus 1, which is less than or equal to 1/2 to the n. So that's our an and our bn. So this guy is geometric with r equal to 1/2, and we know that our geometric series converges if r in absolute value is less than or equal to 1. So this is a convergent geometric series. So we know that this is less than a known convergent geometric series. So by comparison, the sum as n goes from 1 to infinity of 1 over 2 to the n plus 1 converges. So when we're trying to do comparison, is we need to compare, if we want to show something converges, compare it to a known convergent series. And if we want to show that something diverges, we want to show that it is bigger than a known divergent series and therefore diverges. So it's worth noting that when we're using direct comparison, it is often very helpful to compare, as we just saw in this example, to a geometric that we know converges or diverges. The other one that is useful is our P-series test. And if we recall, the P-series test says that the 1 over n to the p converges if the p is bigger than 1, and it diverges if p is less than or equal to 1. So this is also great for comparison. And we'll do some examples to illustrate that as well. Oops. This one. All right. So let's take a look at this. So we want to determine if this series is convergent or divergent. So, as I was just mentioning, this one is going to be a great candidate to compare with a P-series. And the reason for that is if we look at our numerator, it's degree 0. And if we look at our denominator, it's degree 2. So a good candidate to compare that with might be 1 over n squared, because they have approximately the same degree. So now, using our same argument, if we are adding things to the denominator, that is going to make this smaller. So 6 over n squared plus 7n plus 2, or 71n plus 2, is going to be less than or equal to 6 over n squared. Because adding things to the denominator is going to make this fraction smaller. So then this is a P-series with p equal to 2. So then we know that P-series with p bigger than 1 converge. So then, once again, by comparison, the series converges. So at this point, you might be thinking, well, this doesn't seem too bad, and it's not, but the hardest part of any of these tests is going to be picking the right series or being able to pull it out of the hat. Especially when we get to the end of all of these things, you'll notice by the time we get to the end of this, we're going to have a lot of different tests, right? So the challenge is going to be in the later sections when we're not told specifically what test to use and we kind of have to pick it for ourselves. This is kind of analogous to when we were learning how to do integration. At first, we learn all these techniques, and in each section they're not too bad, but then when you have to start just looking at any series and determining if it converges or diverges, it gets a little bit more difficult. So speaking of practicing, I believe the next one is for you guys. So let's go ahead and determine if this series converges or diverges. So first thing we'll note is that adding 1 to the denominator makes it larger. So we know that 2 to the n over 3 to the n plus 1 is less than 2 to the n over 3 to the n, which would then equal 2/3 to the n. And this is going to be geometric with r equal to 2/3. So with r equal to 2/3 on a geometric series, we know that this is going to be convergent. So then, by comparison, the series must converge. So really, for direct comparison, the two best times to use it was with something like this, where it's almost geometric, or when you have polynomials over polynomials like we had in the previous example, and we can compare to a p-series. Because otherwise, there's going to be other tests that we can use. And speaking of other tests, that is where we're going to go next. So the next test that we would like to speak about is the limit comparison test. Well, it's another comparison test, but this time instead of directly comparing the sequences, we're going to compare some limits and see what happens. So the limit comparison test is the next one on our sheet here. And we have the following. So if, once again, both the ANs and the BNs are always positive and not equal to 0, and the limit as n goes to infinity of the ratio of the ANs to BNs is equal to some number c, where c is bigger than 0, then either both series converge or both series diverge. So basically, this is saying if you have two different series that have sequence members that are always positive, and the limit as n goes to infinity of the ratio of the sequences equals a finite number, then those two series share the same fate. And what I mean by that is that they converge together or they diverge together. So if you're comparing with a known divergent series and you get this, then they would diverge. And if you're comparing with a known convergent series, then they both converge. So let's go ahead and take a look at a couple of examples using limit comparison. So example number 2, determine if the series converges or diverges. So if we tried to do direct comparison, we'd find that it's not going to work very well. But this reminds us a little bit of a different series. So I'm going to call this guy AN, or at least the general term. So we have our AN is equal to 1 over n squared, or n plus 1. And I want to do limit comparison with, and we'll notice that this is degree 0 in the top and degree 1 in the bottom. So this is going to be pretty close to 1 over n, which is what I'm going to want to compare this with. And if we remember, I think it was last time, this guy is the harmonic series. And the harmonic series is a known divergent series. Because this is degree 0 and degree 1, so they're about the same for these. So if we do limit comparison, we're going to take the limit as n goes to infinity of an over bn. So that's going to be 1 over n plus 1 all over 1 over n. We multiply by the reciprocal of the denominator, so 1 over n plus 1 times n, which gives us the limit as n goes to infinity of n over n plus 1. So that's type infinity over infinity. So then by L'Hopital's rule, we take the derivative and we have the limit as n goes to infinity of 1 over 1, which is 1. So the value of that limit is going to be 1. So since the harmonic series diverges, we have by limit comparison both series diverge. So if we would have been comparing it to a convergent series, since they share the same fate, then both series would have converged. All right, so let's take a look at our next example. So we take a look at example B this time. And we have the sum as n goes from 1 to infinity of 1 over 3n minus 2. And we look at it and we're like, yeah, it's almost geometric again. But instead of adding 1, we have minus 2. But we can't do direct comparison because 1 over 3 to the n minus 2 is bigger than 1 over 3 to the n, which equals 1/3 to the n. But it's bigger than a known convergent series, so that doesn't tell us any information. So direct comparison does not work on this example because when we subtract something from the denominator of a fraction, we actually make the fraction bigger because we're dividing by a smaller number. So we mentioned that it is almost geometric. So maybe we should try limit comparison with a geometric series. So since it's almost geometric, we can compare to the geometric series 1/3 to the n minus 1, or just 1/3 to the n. And if we do that, we know that this has r equals 1/3, so that's going to be convergent. So if we take the limit as n goes to infinity of, this will be our an and this will be our bn, we're going to have 1 over 3 to the n minus 2 all over 1 over 3 to the n. So once again, we multiply by the reciprocal of the denominator, and we get 1 over 3 to the n minus 2 times 3 to the n over 1, which is the limit as n goes to infinity of 3 to the n over 3 to the n minus 2. And once again, it's type infinity over infinity, but we don't want to use L'Hopital's rule this time because the derivative of an exponential is just another exponential. And if we keep doing that, we'll never make any headway. So we want to factor out our greatest common factor from each the numerator and the denominator. So if we do that, we have the limit as n goes to infinity. I factor out a 3n, that leaves behind a 1, and I factor out a 3n, that leaves behind a 1 minus 2 over 3 to the n. Then these reduce out, and as n goes to infinity, a constant over infinity is going to go to 0. So then this limit converges to 1 over 1, which is just 1. So then, by limit comparison, the series converges. Because 1 over 3 to the n converges. All right. So let's go ahead and take a look at our U. So we're going to want to compare this to our B sub n this time is going to be the harmonic series, which is 1 over n, or a P series with P equals 1. So if we have n cubed minus 1 all over n to the 4th plus 3n cubed minus 7n squared plus 5n plus 1, all divided by 1 over n, we multiply by the reciprocal of the denominator, so that gives us n to the 4th plus 3n cubed minus 7n squared plus 5n plus 1 times n over 1. Finally, putting all that in, we get n to the 4th minus n over n to the 4th plus 3n cubed minus 7n squared plus 5n plus 1. And these guys have the same degree, n to the 4th. So finally, we can factor out that 4th degree, and that leaves 1 over, or n to the 4th times 1 minus 1 over n. And then factoring the n to the 4th out of the denominator gives us 1 plus 3 over n minus 7 over n squared plus 5 over n cubed plus 1 over n to the 4th. Those reduce out, and finally, if we take the limit as n goes to infinity, a constant over infinity is going to be 0 for all of these things, and we finally end up with 1 over 1, which equals 1. So it's worth noting, we could have used L'Hopital's rule 4 times, and 4 derivatives would have given us 4 times 3 times 2 times 1 in each of them, so 24 over 24, which would also reduce to 1. Gives us the same thing. So since 1 over n is divergent, the series diverges by limit comparison.